Hi, my name is Don Bagwell from the Advanced Technical Skills Organization, and this is demonstration number 4 in a series of demonstration videos about WebSphere Application Server for zOS. In this video, we're going to explore data access and alternate failover technologies. It should come as no surprise that applications running in zOS have the ability to access data running in key data subsystems on zOS. What we're going to focus on here are the local cross-memory connectors that are available for accessing that data. Now, it's important to note that this is in addition to normal TCP/IP-based network connectors that you might be familiar with on WebSphere on the other platforms. Those are supported as well, but what we're going to focus on is the cross-memory local connectors. The local connectors for zOS are configured in a fashion very similar to what's done on the distributed platforms. For example, JDBC Type 2, if we take a look at resources, JDBC providers, and we drill into a provider that I created earlier, we see that it looks very similar to what you'd see on WebSphere Undistributed. The difference is the native library path is pointing to a variable that, if we look in the environment variables, we will see points to the location where DB2 for zOS is installed and that native library path. Now, if we take a look at the data sources that are defined underneath that, we'll see that it too is defined in a fashion very similar to on the other platforms. So we give it a name, we provide a JNDI name for the data source, and if we scroll down to the bottom, here's where we see the driver type is defined as type 2, and rather than providing a host and port, which we could if we were configuring a type 4, but we're configuring a type 2. So here we provide the DB2 location name for the DB2 system on zOS. Now, from an application point of view, it's very similar. In fact, it's identical to what it would be for a Type 4 connector. So if we drill under the WebSphere Enterprise Applications, take a look at a deployed JDBC application and drill under Resource References, we will see that the application simply references the JNDI name of the JDBC data source just as it would if it were a Type 4. What about local adapters and CICS? It's a very similar story. If we go under Resources, Resource Adapters, we'll see the JCA resource adapter for CICS installed. If we click on that, we see that it was installed with a defined native library path. And if we click on the J2C connection factories, we'll see the connection factory that's defined. And if we drill into that connection factory and under custom properties, we'll see that the custom properties for this connection factory, the connection URL is defined as local, and the Apple ID is defined as the Apple ID of the CICS region to which this local connector will connect. For an application that would connect, again, we go under Application Types, WebSphere Applications, take a look at a deployed CICS application. The resource references for that, just like for JDBC, it simply references a JNDI name, and in this case the JNDI name is that for the connection factory. And with MQ, it is very similar as well. If we go under the MQ messaging provider for JMS, we see that we have a defined native library path. And if we go under Q connection factories, we can take a look at the Q connection factory that defines the queue manager. We see it has a name and a JNDI name. And for the connection, we name the queue manager and specify the transport as bindings mode. We're often asked, okay, so what's the value of using the local connectors? And the usual answer people give is, well, it's lower latency. And that's certainly true, but we don't like to rest on just that benefit. So I draw your attention to the WP 101-532 document at ibm.com/support/techdocs. And if you go into that tech doc, scroll down, there is a presentation that if you take a look in there on chart 35, there's going to be a list of the benefits that we like to cite for the local connectors and co-location of data and the applications using zOS. Here is chart 35 from that presentation deck, and here are the bullet points that we like to cite for the value of co-location. Latency was one of them that we mentioned. It's also extremely secure. You're going cross-memory. There's no chance whatever to do any kind of sniffing of the data going between the application and the data. And the other bullets you can read down through as well. A lot of them have to do with avoiding overhead associated with network protocols. And the final bullet's an interesting one to dwell on and think about, and that is that when you've got your application server, and data system all within the same operating system instance, you have a reduced complexity for debugging, because you've got every tool and everything is within the same operating system, and it's much easier to figure out what's going wrong as opposed to a topology where connections are hopping across firewalls and routers and all sorts of other things. So these are the items that we like to cite as the benefits of co-location. Another question that comes up is whether or not the local type 2 connectors use more CP than the remote ones do, particularly with respect to GP versus specialty engine. And we'll draw your attention to the WP101476 tech doc that has a performance study that was conducted that measured the processor usage type 2 versus type 4. And I'll draw your attention to the update study results PDF, and we'll take a look at a particular picture in there that tells a very good story. In that WP101476 update tech doc, there is a picture on page 1 that shows the results of the measurement of type 2 local versus type 4 remote for this particular workload. And the red bar shows the GP usage, type 2 versus type 4, and you'll notice it's essentially the same. And if you take a look at the green bar, that's the ZAP specialty engine, and the blue bar is for the ZIP specialty when using type 4. And type 4 is, of course, coming across DDF, and that's where the ZIP usage is coming from. So if you add up the green bar plus the blue bar, you see that the total specialty engine usage with type 4 is actually more than the specialty engine usage for type 2, and the GP usage is essentially the same. The purpose of the alternate JNDI function is to provide a backup connection pool in the event your primary connection pool suffers get connection failures. So imagine you have a scenario where you are using an application that's connecting with local connectors to a local data source, and better still, imagine this is in a parallel sysplex in a data sharing group, and imagine that your local data resource were to go away. What alternate JNDI then does is it automatically fails over to the alternate JNDI connection pool, transparent to the application, and if that is defined as across TCP to one of the surviving data resources in the data sharing group, your application can still get access to data. To see how this works, let's first review our configuration. Here I'm showing the JDBC data sources. There is the type 2 data source to our local instance of DB2, and then there is another data source that is defined as type 4 to a DB2 instance in another LPAR in the Sysplex data sharing group. Let's go into the type 2 data source, and let's look at the connection pool properties, and then the connection pool custom properties, and here we'll see 3 custom properties defined. The failure threshold custom property defines how many get connection failures must occur before a problem is detected and the failover to the alternate is enacted. The alternate resource JNDI name property defines the alternate data source, and in this case we're showing that to be the type 4 data source. And the resource availability test retry interval property tells WebSphere how frequently to poll for the return of our primary data resource so that it can fail back. Next, let's take a look at the application and its resource reference definition. So if we go in there, we see that the data source that's defined to the application is our primary data source. This is the local type 2. And this is a key point. The application has no knowledge of this alternate JNDI failover function. That's all transparent to the application. All the application knows about is its primary JNDI. The other functioning is behind the scenes. Let's watch this function in action. Here we have the application, very simple servlet application that selects, inserts, and deletes records from DB2. We're going to first select to show there's nothing in the table. We'll go back. We'll insert records into the table, 10 records inserted. We'll come back, and now we're going to switch over and kill DB2 to simulate a loss of our local DB2 resource. Here we are at SDSF-DA showing the active DB2 address spaces. We're going to issue a DB2 stop with the mode of force to kill it really quickly. And there it's gone. We're back at our application. We're going to issue a select, and we should see a failure this time. And there it's saying there was a problem. So we're going to go back, try it again, and we see another problem. So that's our 2 failures. Now the next select should work, which means that it's failed over to the alternate and gone to the remote DB2. And there we are. If we go into the held output of the server controller region, we see a message that indicates that the failover occurred. We see it right here. The configured primary resource with the JNDI name of type 2 DS is unavailable. New requests will be routed to the configured alternate resource that has a JNDI name of type 4 DS. If we restart DB2 and wait the period of time that we specified on the retry polling interval, we'll see a message that comes out that indicates that the local DB2 has returned, and here's that message. The configured resource with JNDI name of type 2 DS is available to process new requests for the resource with a JNDI name of type 2 DS, which means that any new GET connection requests that are made against that application will now go back to the primary. Any existing connections still flowing across the alternate type 4 will continue to flow across the type 4, but all new will now go back to the type 2. Now imagine you wish to manually fail over so that you can do some maintenance on your local DB2. The way you accomplish that is with a zOS modify command, and you see the example here, failover, comma, and then the primary data source JNDI. That will invoke the failover. You'll see the message saying that failover has completed successfully. When you've completed your maintenance and you want to fail it back to the primary, you issue the failback command, again with the primary JNDI, and the failback will be processed. There's another connection pool custom property exclusive to WAS on zOS that indicates what action should be taken when both the primary and the alternate data resource is unreachable. And there are 3 options here, 1, 2, and 3. 1 is take no action. 2 is to issue the pause listeners command against the application server so the listener ports go dark. And the value in that is that front-end routing functions can then see that that server is no longer available in a route elsewhere. And option 3 provides the opportunity to shut down just those applications that are using the primary data source that has gone unavailable, but other applications that presumably are still working fine can continue to work. Let's see both number 2 and number 3 in action. In this scenario, we have the failure notification code set to 2, which means pause listeners will be invoked. We'll reach the failure threshold of 2 by issuing the select twice. There's the first with a failure. There's the second with a failure. And now the third time we'll issue it, we see a blank screen. That's because the listener ports are gone. Let's go over to 3270 and see evidence of those ports being dark. And here is the output for the controller region indicating that the listener ports have been shut down. Now it's important to understand that the server is still up. It's just that the ports themselves have been closed. So if you've got work in that server that's continuing to process, that work will continue to completion. It's just that no new work will be taken on because the listener ports are dark. And here's the scenario where the failure notification code is set to 3, which means that the listener ports will stay up, but any applications using the failed data source will be taken down. So let's again drive the select twice to see failure. There's the first failure, there's the second failure, and now when we drive the third, we should see this error, which is indicating the application is gone. If we go over to the admin console and look under applications for all applications, we will see that indeed the JDBC application we were driving has been stopped, but the other applications in the server are still working. And that's the end of this video demonstration in which we looked at the configuration of local data connectors and saw it's very similar to how it's done for remote type 4. We took a look at the alternate JNDI failover to type 4 when that's pointing to another LPAR, ideally in a data sharing group in a parallel sysplex. We looked at the modify failover and failback, which is very handy when maintenance is planned. We took a look at the failure notification code, which provided two options. The first one would issue an automatic pause listeners to close the listener ports on the server if none of the configured data resources was available. And the other one was an automatic stop of the application when no data resources were reachable, but other applications in the server remained up. More zOS demonstrations are available in the other videos.